In video 52 of Tensor Calculus, we're going to make use of the Levi-Civita symbols to define and analyze a vector operation known as the cross product. What you see here is the Tensor Calculus definition for a vector operation known as the cross product. We've got two vector components, uj and vk, multiplied together. And we learned in the last video that our Levi-Civita symbol here is also a tensor. Therefore, we've got a product of three tensors, and therefore this expression is a tensor. Now, if you look at the index structure, you'll see that j is a dummy index, k is a dummy index, but I is a free index. And therefore, we have it on the expression on the left-hand side here. So what we've got is an operation that combines two vectors, u and v, together as a tensor product like this to create a new vector, w. And of course, as with any vector, we could also express it in covariant terms like this. We can simply lower the free index I, and we can swap indexes j and k from upper and lower positions as you see here. So either one of these expressions is a valid representation of our operation known as the cross product. Now, as with any vector components, we can use these expressions to create linear combinations. So we could say that our vector w would be equal to either one of these expressions combined with the appropriate basis vectors. So we could use epsilon ijk, uj, vk like this, combined with a covariant basis vector of zi, and this forms a full contraction and therefore an invariant expression. We could also use the other definition here, epsilon ijk with lower indexes, using the upper indexes for each of the vector components, and combine those with a contravariant basis vector like so. And that's also an invariant expression. Now I'm guessing that you have probably seen the cross product in another form. You've probably seen it written like this, a vector w being equal to vector u with a cross symbol here and v like this. This would be known as the dyadic form of the cross product, one that you're probably already pretty familiar with. So now let's explore some of the properties of the cross product. We'll start with the expression for the cross product right here. The first thing I want to do is to rename a couple of indexes. We have dummy indexes j and k, so I'm going to rename j to k and k to j. It's going to look like this. We'll have epsilon I kj and u k vj. All I've done is to rename the indexes, nothing else. Okay, now I want to switch the order of the k and j indexes right here. And of course, when I do that, I have to change the sign. Our Levi-Civita symbol has skew symmetry just like our permutation symbols. So if I do a single flipping operation of the indexes, I have to change the sign. Now for these two factors, I just reverse the order. The multiplication is commutative, so I can put these factors in either order. So I'll put them like this. I'll put vj and uk like that. Okay, now what do we have? Well, if you compare this expression with this one, you see that the only difference is that I have a different order of these two factors right here, and I have a negative sign. What that tells us is that the cross product of u and v is not the same as the cross product of v and u. If I switch the order, I get a negative sign here. In other words, this cross product operation is not commutative. When I switch the order of the elements in it to v cross u, it's not equal, but it's equal to the negative value like this. When I switch the order of the factors, I have to change the sign like that. All right, moving on, let's see what it means to take the dot product between w and vector u, like this. Now to do that, we would start with our expression for the cross product, as we have shown it up here. Now, in tensor calculus, if we're going to form a dot product, what do? Well, we have to form a contraction between the two components, one covariant, one contravariant. So to form the dot product with this expression, we have to add a factor of u with the I index so that we have a contraction of I here. And now we have a fully contracted expression, which is the dot product. Okay, so where does this go? Well, what I want to do this time is to rename indexes I and j. I'll rename I to j and j to I. Again, just a renaming operation, so nothing changes except the index names. So we have epsilon jik, we have ui here, vk, and then uj out here. Done nothing except rename the indexes. Okay, now the next thing I'm going to do is to change the order of I and j here. And when I do that, it's a single flipping operation, so I've got to insert the negative sign. So we have negative epsilon I j k, and I'll change the order of the factors here. I'll put the ui term last and the uj term first. So we'll have uj, vk, and ui like that. Okay, now what you'll see is that this expression and this expression are exactly the same except one is negative. And we've seen many times that whenever we have an expression that is equal to its additive inverse, equal to its negative, the only way that's possible is if the whole thing is in turn equal to 0. That can't be true unless that's equal to 0. In other words, the dot product between vector w and u is equal to 0. And that in turn means that vectors w and u are orthogonal, or they're at right angles to one another. Okay, well, what about the dot product of vector w with vector v? What's that going to look like? Well, we go through exactly the same exercise as before. We start with our expression for the cross product of u and v. And this time we have to form a contraction using our vector v. So we're going to have a factor of vi this time to form our contraction with I. So same sort of exercise. We're first going to rename indexes. This time we'll rename I to k and k to I. So we'll have epsilon k ji times uj vi vk. Again, doing nothing but renaming indexes. Now I'm going to switch the order of k and I. And because of the skew symmetry, when I do that, I've got to change the sign of epsilon. So this changes back to ijk because I swapped the order of I and k. And I'll change the order of the two factors, uj, vk, vi. And again, as before, you see that this term is equal to its additive inverse, like this, or the whole thing has to be equal to 0, which means again that the dot product this time between vector w and v is equal to 0. So w and v are perpendicular to each other or orthogonal. So our cross product is such that our vector that's created here, vector w, is perpendicular to both vectors u and v. Now that also means that if we look at the plane that's defined by these two vectors, we take vectors u and v, and that'll create or define a plane. Well, then vector w is perpendicular to the plane that is defined by these two vectors. So now let's derive an expression for the magnitude of our cross product. And of course, to find the magnitude of any vector, we just find the dot product of it with itself. So here we need to find the dot product of w with itself, and that means forming this contraction. Okay, so the first term here, using our definition, is just epsilon ijk with uj and vk like this. And then the second factor is going to be epsilon with an I here. But this time I cannot reuse j and k because I'm already using them as dummy indexes in this term. So I need new letters here. We'll just use the letters s and t, and then we'll have us and vt with lower indexes like that. Okay, now in I believe it's video 45, you'll remember that we can express the combination of these two factors, epsilon ijk and epsilon ist, as our delta term, delta ist ijk, like this. All right, that in turn can be expressed this way, delta sti jki. And what I've done is just to reorder the indexes on the top and bottom the same way. I can always reorder the indexes in the top and bottom of our delta expression any way I want to, as long as I do the same thing in both the up, top, and bottom. So I've simply bumped s and t to the left with I on the end, so I bump j and k to the left with I on the end. Now you'll remember, I hope, in video 45 that this is one of our identities. We have a contraction with I, so this is simply equal to delta st jk. And that in turn, by definition, is equal to delta sj delta tk minus delta sk and delta tj. All right, so we're going to replace the product of our epsilon factors here with this last expression. Next, we'll distribute this term and this term to this one. So we're going to wind up with two terms here. But when we distribute this factor to this one, we're going to have index j, which is absorbed, leaving us with index s, and k is absorbed, leaving us with index t. So our first term here is going to be equal to us vt and us vt like this. So that's our first term. Now when we do the same thing with the second term, when we distribute this factor in, first of all it's going to be negative, but this time the k index is absorbed here and the j index is absorbed there. So that's going to give us an expression of negative ut vs us vt like this. All right, let's look at what we have here. This expression right there is simply the dot product of w with itself, which is the square of the magnitude of our vector w. Well, if you combine this term right here with this one, we have the magnitude of vector u squared. You combine this factor with this one, we have the magnitude of vector v squared. It's the dot product of v with itself. This is the dot product of u with itself. Now, in this second term, this factor right here combined with this one is the dot product of vectors u and v. Well, this factor and this one is also the dot product of vectors u and v. So that means that our expression really looks like this. The dot product of u and v, of course, can be represented as the magnitude of u times the magnitude of v times the cosine of the angle between them. So this expression in turn can be this, the magnitude of u squared and v squared minus this term, which would be the magnitude of u times the magnitude of v times the cosine of theta. And of course the whole thing is squared, so each of these factors would be squared like that. Well, we can simplify that to be, we can factor out these two scalar factors here, magnitude of u squared, magnitude of v squared, times 1 minus the cosine squared of theta, which of course is magnitude of u squared, magnitude of v squared, times the sine squared of theta, or the final result being that the magnitude of our vector w is equal to the magnitude of u, we're simply taking the square root of both sides here, times the magnitude of v times the sine of theta, where theta is the angle between the two vectors. And that then is the expression for the magnitude of the cross product between u and v. Now as we work our way through each of these properties, I hope you're beginning to see the power and simplicity of our tensor calculus syntax. Now, proving each of these properties by other methods can prove to be very difficult, but with tensor calculus they are almost trivial exercises. Not only that, but since everything we've done here is in the form of tensor equations, that means that we know at the same time that all of these properties are valid for every coordinate system. So as a further illustration, let's move on and derive yet another important relationship. So what we want to do is to look at this expression, u dotted with the cross product of v and w like this. Okay, well, let's express it in tensor calculus form. It's a dot product, so we'll start with the component of ui like this, and we need to contract that with the expression with a lower index of I, so we're going to have to use this form for our cross product, I j k times v j w k. So this is the tensor calculus expression for what I've written down up here. So now we're going to do some index renaming. I'll just write down the factors first. We'll fill in the indexes here in just a minute. So we have these terms. And what I want to do is to rename I to k. So this will be a k, and so will this. I want to rename j to I. So this is I, and this is I. And I'll rename k to j. We'll have a j here and a j there. Okay, now we'll rearrange the terms. I'm going to put vi first, and then I'm going to have my epsilon factor, and then I'll put wj next and uk last like this. But with the epsilon factor, notice this, that epsilon kij would be equal to negative epsilon I kj. We just flip the first two indexes, but then if I flip k and j, I'm back to a positive expression for I, j, and k. In other words, this expression equals this as a result of two flipping operations. So what that means is that our index structure up here is now I, j, k again. And if I group those together, it's very easy to see that what we've really got here is an expression that's the equivalent of this. This is the dot product of v with the cross product of w and u, like so. Now we can go on to repeat the process if we want to show that this is also equal to the dot product of w with the cross product of u and v like this. Okay, now this again is an illustration of something that's very hard to prove by other methods, but with tensor calculus it's a very easy exercise. So with all that, let me wind the video down by showing you the geometric significance of the cross product. Suppose we have two vectors, v and w, drawn in a three-dimensional space, and v is a vector that's going to be pointing to the right here. W is pointing backwards into the page and to the right. So again, this is supposed to be a three-dimensional diagram here. Well, if we're going to take the cross product between v and w, it's going to look like this. And to establish the direction of v and w, remember we said that it's perpendicular. The cross product is perpendicular to each of the two vectors. So it's going to be perpendicular to v right here. And then it's also perpendicular to w, which is going back into the page, as I say. Okay, now to establish the direction, we use the right-hand rule. And the right-hand rule is that you point your index finger in the direction of v, and then you point your middle finger in the direction of w, and then when you do that, your thumb is going to point in the direction of the cross product, like this. So note in particular that v cross w is not the same as w cross v. We made that point during the discussion. W cross v is going to point downward. You'd point your index finger in the direction of w, your middle finger in the direction of v, and your thumb then would point downward like this. So these two products are not the same. It's not commutative. They're negatives of each other, which in vector terminology means they point in the opposite directions. Next, let's drop a perpendicular from the tip end of vector w back to v here. This dashed line is perpendicular to vector v, and because the angle between the two vectors is theta, and this is a perpendicular line, then the length of this line segment we've constructed would be equal to the magnitude of vector w times the sine of theta, which is the angle between the two vectors. You know, the sine is the opposite over the hypotenuse, so that makes the length of this leg right here equal to the magnitude times the sine of theta. Okay, well, you'll remember we derived the fact that the magnitude of our cross product here is equal to the magnitude of vector v times the magnitude of vector w times the sine of the angle between the two. All right, so if we were to multiply the magnitude of vector v times this segment we've constructed, which is w sine theta, then this is the magnitude of the cross product. Well, the product of these two line segments is nothing more than the area of this parallelogram that you see constructed here. So this is a very important geometric result, and that is that the magnitude of the cross product is equal to the area of the parallelogram that is constructed as a result of the two vectors. Next, let's add a third vector, vector u. Now u is going to point to the right and back into the page. It's also pointing slightly upward. It's the tip of it is going to be above the plane that is defined by v and w here. To get a sense of that, we'll drop a perpendicular from the tip of u down to the plane that is defined by v and w here. Now, if the angle between u and our cross product is phi, then the length of this segment is going to be u cosine of phi. You get a sense of that by completing this little door shape here. Then this side over here would be the adjacent side of this triangle relative to phi. So this side divided by the hypotenuse would be the cosine of phi. So that means this length as well as this length is equal to u cosine of phi. Okay, well, now let's complete the diagram by constructing parallel segments like this to form a parallelepiped. So now we have a solid figure, and this vertical line that we've been talking about is the height of this parallelepiped. So the volume of the parallelepiped is going to be equal to the area of the base, which we've already determined up here, times this height, and that's going to give us the volume. Well, this height is u cosine of phi, and u cosine of phi times the magnitude of v cross w over here is nothing but the dot product of vector u with the cross product. In other words, this relationship holds true. The volume of this parallelepiped is going to be the dot product of our new vector u with the cross product of v and w, because this volume is going to be the magnitude of u times the magnitude of our cross product times the cosine of the angle between them. So this expression is what we'd get if we multiplied u cosine phi times the magnitude of this. So that then is the geometric significance of the cross product. The magnitude of the cross product is equal to the area of the resulting parallelogram, and the dot product between u and the cross product is going to be equal to the volume of the resulting parallelepiped. What we've done in this video is to define an operation known as the cross product. The cross product consists of two vectors, u and v in this case, combined with the Levi-Civita symbol, thus producing yet a third vector. Now we know it's a vector because each of these factors is a tensor, and thus we have a tensor product with a single free index of I. Now, as with any vector, we can represent it as a contravariant component or a covariant component like this, and we can use either form combined with the appropriate basis vector to form an invariant expression of the vector in this form. So what we have is the tensor calculus equivalent of what is more commonly recognized as this in its dyadic form. Next, we derived a couple of basic properties of the cross product, the first being that the operation is not commutative. Because of the skew symmetry of our Levi-Civita symbol, it became immediately apparent that changing the order of the multiplication here resulted in a change of this sign. So the cross product of u with v is not the same as the cross product of v with u. What we discovered is that the magnitude of the results is the same, but as vectors they point in opposite directions. We then dotted the cross product with vectors u and v respectively. And because of the skew symmetry again of the Levi-Civita symbol, we quickly discovered that the result is 0 in both cases. Now that means that our cross product is orthogonal to both vectors u and v and is thus perpendicular to the plane defined by those two vectors. We then dotted the cross product with itself in order to derive its magnitude. And of course that means that we had to combine the covariant definition with the contravariant definition like this. Now, by combining this factor with this factor, we were able to make use of our delta system to reduce the expression to this form. And what we see from this is that this dot product is really the square of the magnitude of our cross product. Over here we've got this factor combined with this one, which produces the square of the magnitude of vector u, and these two terms together form the square of the magnitude of vector v. In the second expression, these two factors together are the dot product of u and v, and these two factors together are also the dot product of u and v. So that gives us the dot product of u and v squared. And finally, the definition of the dot product itself, combined with a simple trig identity, led us to this very concise result. And finally, we dotted the cross product with a third vector, and again making use of the skew symmetry of our Levi-Civita symbol, we were quickly able to recognize that this is an invariant expression that can be represented in any of these three ways, or in the equivalent dyadic form that you see here. We also demonstrated that each of these forms is an invariant expression which represents the volume of a parallelepiped defined by these three vectors. In the next video, we're going to make additional use of the Levi-Civita symbol to define a differential operator known as the curl.